Hello, everyone. My name is James Laughead, and I am a May 2022 graduate from The Ohio State University with a Bachelor of Science in Statistics. I'm currently looking for a full-time analytics role and have been applying to these positions for the past several months. Looking at my resume, one thing I noticed that was different from mine than my peers who had already gotten jobs in their respective fields was that they had either a prior internship or full-time position. And so I was thinking to an employer, what exactly does that mean to them? And in my opinion, a candidate with prior experience demonstrates a certain amount of confidence to employers that they'll be able to perform the necessary job functions and other duties of the job. So that's the conclusion I came to why employers prefer candidates with prior experience as opposed to those that don't have that experience. And so that's why, in place of that, I decided to introduce my own statistical concept in order to show employers some of what I'm able to bring to the table, as well as my process of thinking. And before I talk about this, I want to say that in no way is this a proof or a theory. It's more of, I would describe it as a way of thinking and based rooted in statistical theory. You'll understand in a little bit when I start going into the actual idea itself. And so this idea, I call it the assumed probability, and I'm going to be comparing it to the standard mathematical probabilities, which you would see in Bayesian statistics. What I mean by that is you flip a fair coin, and the probability of heads is one half, and the probability of tails is one half. That's the sort of, when I talk about Bayesian statistics, is those kind of statistics. And so, and when I reference the mathematical probability, that would be like the true mathematical probability as stated in Bayesian statistics of uh, the three axioms that like all the probabilities have to add up to one, and no less or greater than that, and that kind of stuff. And so the assumed probability is like the mathematical probability, except we will be removing mathematically possible events which have never occurred before, and comparing that to the mathematical probability. To illustrate this and the potential benefits of using the assumed probability, I've created an example. So the example we're going to be using today is the Powerball lottery. It is a lottery game which has been going on since the 90s, has drawings 3 times per week, so there are thousands and thousands of collected data points. So I'm just going to go in a little introduction on how the Powerball game works in case someone doesn't know. So in the Powerball game, 5 distinct numbers from a possible 69 distinct numbers are chosen, as well as there's a separate red ball between 1 and 26 inclusive, and the red ball and then the 5 other balls together determine the winning combination for the night, and that would be the jackpot prize. And so the odds of selecting the exact Powerball combination are, and I'm going to be editing some numbers on the screen to make it easier for viewers, are combinations 69 taken 5 at a time, which is 11,238,513. If you wonder why I keep looking down, I have my own personal notes when I've been doing some of these calculations on there. Multiplied, so 11,238,513 multiplied by 26 for the 26 possible red ball combinations for a probability of 1 in 292,201,338 of winning the jackpot in an individual ticket. And I looked this up on Powerball after the fact, and that is the odds stated on the Powerball website of winning the jackpot. So that's how I know I did the calculation right. Um, that means the mathematical odds state, or the mathematical probability state, that the probability of winning the next drawing on a single ticket would be 1 in 292,201,338 as well. So, however, with the assumed probability, I'm going to be taking out cases for the next drawing which have never happened. And there's a few different ways I believe you could do this, but I'm just going to only illustrate one. And so, in the data which I have observed, now I want to say that it's hard to find Powerball data from the 90s, but from all the data I have observed, there have been no instances where 4 of the 5 white balls remained the same as the previous drawing. And so this means that, so let's say we have a probability drawing, like any random Powerball drawing, for the very next drawing. That's where we're going to take what's going to be the assumed probability of winning for that that drawing. And so you might think, oh, the lottery, that's not very applicable. Well, this is just an example to sort of demonstrate some of the thinking, and then we're going to be getting into some of the real industry applications. And I have 4 industries which I have identified where this sort of thinking is applicable. And so, again, I'm just going to state that we're going to say that from all the data I've observed, there has not been a drawing where 4 out of the 5 white balls remain the same as the previous drawing. So we are going to remove those from the probability calculations until it happens. That part is very important, and I'm going to be explaining that later. So the amount we can subtract out from the probability would be combinations 66 taken 2 at a time, because with 3 balls, so there's 69 total. So if you have 3 balls that are the same as the previous, there's 66 total balls that it could be for the other 2. So that's why it's 66 options taken 2 at a time, and that equals 2,145. And then multiply this by the amount of possible red balls. So you get 2,145 times 26 for a total of 55,770 of those outcomes you would remove. And so we subtract this from the 292,201,338 in the mathematical probability to get the assumed probability for the next drawing would be 1 in 292,145,568. And so now you may be looking at this and think, sure, your odds are better, but it's still such a long shot to win. But what's important in this is the sort of percentage I've gotten closer to winning utilizing the assumed probability as an optimization tool. And so we will be doing this by setting up a proportion. And so we're just going to, and I'm going to put this on the screen too because there's some big numbers. We're going to do a proportion, so it's going to be the assumed probability divided by the mathematical probability. So it'd be 1 divided by 292,145,568. So the assumed probability we calculated divided by the mathematical probability that is stated on the Powerball website of 1 divided by 292,201,338. And that proportion equals 1.0009190. And if you would convert that to a percentage, so you would, if you convert that to a percentage, it would be 0.19% better, basically. And so you might be thinking that again doesn't seem like very much, but this is the proportion of how much better my odds of winning, again, using the assumed probability. But imagine applying this to a company that generates $50 billion in revenue per year. So using let's say a company uses an optimization principle such as this one for all across the board in their entire company or in many aspects of their company. So if you, for a company that generates $50 billion in revenue, if you in order to get what the with these optimization principles, how much better you're doing, you'd multiply 50 billion times this number that we got after doing the proportion, and their total revenue would be 50 billion 9,000,000 544,899. So we're just going to round about 9.5 million more in revenue. And so that might not seem a lot compared to 50 billion, but in more realistic terms, that money might be 100 employee salaries, which the company did not have before. So after hearing this, there's a few things I want to address about the assumed probability. And the first is what happens if like there's a case, like so we removed some cases, but let's say what happens if there is a case where in two consecutive lotteries, four of the five numbers in the set of five are repeated. Well, in the assumed probability, we would just remove that from the assumed probability, and the assumed probability would then get closer to the mathematical probability because there'd be less that we could remove that from it's things that have never happened before, and but there will still be some. So in that case, the assumed probability just gets closer to the mathematical probability, and I'm going to explain a little bit more about that in a different application with respect to time, because there's a similar application with respect to time. So you just kind of add back in those ones that you removed for if cases like such as that happen. So if the cases that you removed that had never happened, like a certain group of cases, and then it actually did happen, you just add it back in add it back in and don't remove it when you do your assumed probability calculations. And so here's another thing that I want to address is someone might be thinking, oh, you can just do computer simulations and you can find that, let's say you do a computer simulation of 10 million and after 300,000 the 300,000 iterations you get that there was two cases where the set of five there's four that repeated. And so that is something that you can do computer simulations, but for this specific example, if you look at what that would be in real time, so we're saying 300,000 out of 10 million iterations. So that's at the very beginning of those iterations, the 300,000 mark. So, but even so, the 300,000 mark, if 300,000 drawings take place in real time, that is around 300 years of real time in lottery drawings. And so that I feel gets to the point where it becomes to get beyond the relevant scope of time. So that's why I think that you are able to do computer simulations and kind of see what it would be, but I don't think that those necessarily invalidate this sort of idea of assumed probability, just given the scope of time and the relevance of time. Like I don't believe 300 years in the future an event happening is in the relevant scope of time. And so now we have defined our optimization principle. So this is my own optimization principle that I came up with. A little bit later, I'm going to describe a few things that this principle, the assumed probability as I call it, is similar to, but I've really never come across anything that was exactly the same. But there are two things that are sort of similar uh, concept wise, and I'm going to be describing those at the end of the video, sort of what I was thinking about. Um, and so, with the opposite optimization principle of assumed probability, this essentially gives us margins that are slightly better in decision making. And for large scale companies, medium scale companies, that could mean the additional revenue of millions of dollars, as I described in the the general company that makes $50 billion example. So it's this principle is more an optimization principle. If you're able to do things that much better, like just a little bit better, then you'll be getting in the long run, over courses of a year, 2 years, 3 years, you'd be just getting that much more revenue that they did not have before. And now I like to get into where this is applicable in sort of more real life industries. So there are four industries right now that I've seen that are that this idea is applicable in. And so I'm just going to kind of go through the different things I was thinking about and different ways that this optimization principle would be applicable in different real life settings. So this is where it gets sort of the real life settings. The example is just kind of to demonstrate from a mathematical standpoint, oh, like, so this is how much better this optimization would be with that and what sort of revenue it could lead to. Now we're going to be getting into the applications in different industries. And so the industries I found this concept to be the most applicable to are the more rates-based industries. And by rates-based industries, I mean insurance, real estate, and banking. And the rates, so obviously everyone knows insurance rates, real estate, meaning the rates that you can rent out properties for, and banking, such as credit card rates, loan rates, and that sort of thing. And so for instance, the rates that should be given to, so we're going to talk about insurance. For insurance, this principle can be used to more accurately determine the rates that should be given to individuals based on external factors. And this is just from what I've seen. Obviously, I do not work at a company right now, or an insurance company, or any of those companies. I do have a job right now, but I don't work at one of those companies. I kind of have a local teaching job after school for the local school district. So I don't have a corporate job where I know kind of what they do. And so I've been able to see on the internet different things that different companies do. So perhaps maybe companies have tried something similar to this, but for me as an individual, there's no way for me to know. So I'm just going to be describing different applications that I see that companies may or may not be doing. And so we're going to be, for this principle can be used to more accurately determine rates that should be given to individuals based on external factors. And I'll be going in some examples. So let's say if there is a location which regularly floods, like let's say this location has had floods, like major flooding at like once a year, like a certain location, major house flooding once a year. So basically, when you're assigning rates to those individuals that are wanting home insurance for that, basically you can sort of eliminate a range of rates that does not include premiums for floods. And you might be thinking, oh, there are floods. So how you're talking about the assumed probability, and that's talking about things that have never happened, but you have to kind of look at it from a step back. So let's say there is a flood. There has been flooding in a region. Every year, major flooding is like major damages that the insurance company has to pay out. Saying that there has been that means that there has not been no floods. That is kind of more what we are looking at, that there has not been no floods. And so that's why you're able to sort of remove that set of rates that does not account for flooding incidents, considering that every year there has been one. This is just a theoretical example. Um, and so you might be thinking that this might seem unfair to customers at first, but I believe that if rates are able to be given more accurately, meaning like more accurately for the rates, so that more accurately the amount you're paying, and also the amount of coverage that it can cover, because rates are a two-way thing. You For insurance, you pay a certain rate, and in response, if something happens, your house floods or just some damage, then you get paid out by insurance. And so it's accurately establishing those rates that would be more beneficial for the company, as they don't want to, they want to make money obviously, but they don't want to having to be losing big amounts when they have to pay out certain individuals. And it's beneficial to individuals because they want to have rates where, if there is they want to have rates where, first of all, it's affordable to them, but second of all, if something does happen to their house, they get paid a appropriate amount of compensation, that they're able to sort of maintain the same lifestyle at the same house, that sort of thing. So that's why rates, it's a both way thing with rates, customer and the insurer here. So yeah, I got to read through my notes because I just kind of talked on the fly there for a while. So yeah, that could be for let's say insurance. There's many things like you can look at, oh, if there's always been a flood in this sort of area every year, then the rates should be a certain, that it kind of remove the range of rates from the question that is for no flooding, because there's never not been a flood. And for another example, let's say there's a region where there's high crime. So there's consistently been high crime in a certain area of large value, like large value crime. And so you're thinking, okay, so it's not necessarily assessing that there is crime or that there is crime. It's more saying that there's never, let's say there's never not been major crime of theft, major theft in this specific region for this time frame. Let's say every year it's been known that there is major theft. So that kind of would you can kind of eliminate a range of rates that does not account for that, and the more accurate rate of range of rates would already be including that enough like premiums to have coverage for, in case of there are robberies and thefts, and you have to get paid out for that. And yeah, so that's insurance. And so the next industry that I think this could be applied to is like cases of home, or no, it's like cases for real estate. And so in real estate, that one's kind of interesting, because we're talking about real estate. A company may be thinking, okay, what's a property rate let's talk about renting. What's a property rate at which we can rent this property that's profitable? That is, I would consider, the very base level. But I believe it goes deeper than this. So what we need to do more accurately in assessing sort of what the rate should be set at would be, what is a rate that they can charge which will bring renters who are able to regularly pay on time? Okay, that's good. That's kind of the second step. Going even further, what rate can you charge where you can get reliable renters but also have money to make improvements on the property, make improvements on the property, and what should be the rate after these improvements. So you're kind of thinking of these different rates. You're thinking, okay, you have a rate, but like what's a fair rate? What's the rate that could be getting individuals, and what rate should we be charging in order to be able to make the improvements on the property? Um, and so with all the data that's available, I think um, you'd be able to sort of use the assumed probability and um, be able to establish rates that are you're able to improve on slightly, and by doing that, you would be able to uh, kind of invest more in the property itself, and then what should those rates be? So it's all rates based, um, and different things like that. Um, let's see, where was I in my notes? Okay, and then the last one I have is sort of is banking, is the banking industry. It's like in banking, what should be the sort of rates for customers who always pay their loans on time versus those that are late every now and then versus those that are regularly late. And so this is being able to set these rates in a way which is fair to customers, but also obtains the least amount of risk, is sort of the key to the future of rates-based industries, I think. And so let's say the example for banking. Obviously, you could have maybe a sort of a flat interest rate on people that have never missed a payment and they have a certain history and stuff like that. But you start getting into when people have missed, oh, they miss every now and then, they get sort of a different rate. And people that miss more often than not, they're late more often than not, they get a certain rate. And so it's interesting to see kind of be able to assess among the industry what's fair, and maybe they can adjust their rates for different customers in sort of a different way. Because that's I don't know much right now about how exactly like the exact calculations that go beyond behind what's the credit card rate you get, what's the loan rate. I know it involves credit score, but it's just kind of assessing that, and then assessing like sort of the history of the applicant. And oh, this applicant has this part of their history, or stuff like that, or like the applicant, oh, they've never been late. That's like the assumed probability. Okay, so they've never been late. We're not going to give them those sort of premiums. Or if the uh, client has, or the customer has been late, let's say they've never had a quarter, so 3 months, they've had every single rate on time. And so, and let's say they have a history of 5 years of that. So, as a sort of banking company that you're assigning this rate, you're not necessarily going to assign the rate that you're just going to assume that they have a quarter that they pay everything on time, because it has never happened yet. When it does happen, they're able to establish confidence, and you may be able to return to that. But if that has never happened, then the more accurate rate would be, okay, so that's never happened, so we're going to start with kind of removing that range of rates, and then going to ones that, okay, this is what has happened. And so this is the final industry I'm going to talk about, for which sort of the assumed probability optimization can be relevant to, is, and this is a more broad one. So this is a company that either specializes in shipping, or a company that does a lot of shipping products, such as big box stores, for example. So with shipping, the areas we have to assess with the assumed probability would be different shipping routes. And so I'm going to give an example. So suppose that a shipping route has always had delays in certain parts of the country during certain times of the year. So this means, in other words, there has never not been a delay. We're going to talk about just major delays. There's not been a major delay in specific areas. So then we can utilize the assumed probability while preparing for these routes and already sort of plan for delay. And let me go a little bit more. I'm going to go a little bit more in depth. So let's say there's a history. Let's just say all time. There's never not been a delay. Then you already plan for this delay. And now with this in mind, so let's say there's never. So you're already planning for the delay, basically. Now with this in mind, it's up to the analysts if the original route should be taken or if perhaps a new route should be utilized, traveling to different areas in order to reduce the gas cost and be able to ship products more efficiently, which helps stores out because they're able to sell more products on their shelves. And so I'm going to get a little bit more in depth when I talk about time. But for the shipping industry, that's another thing for that time is very relevant for. And when you're talking about never not happened, let's just say things that have never not happened, that we've already addressed that in the assumed probability. But what's important is also addressing, let's say, there's never not been a delay in the last 10 years. So perhaps before that, it was smooth sailing, no major delays. But in the last 10 years, there's never not been a delay. And so you might be thinking like, okay, but that's new data, and the most recent data is the most relevant. If there's never not been a delay in the last 10 years, you got to start thinking about, well, why is that? There's more cars on the road. Maybe the roads change. The roads are different. Like there's construction constantly, or the roads, some of the lanes are just bad, so people don't use them as much. So it's like you got to really think about a lot of those things. But with respect to time, that's why I'm going to talk about the assumed probability with respect to time right now. And so I guess to wrap up the industries, so there are probably more industries in which can benefit from the assumed probability thinking, and I think of it as sort of an optimization principle of how can we do things a little bit better? How can we do things a little bit more accurately? And that more accurately, that helps customers and like employers or customers and the like suppliers of the industry, like the insurance and stuff like that, and the banks and the real estate people and stuff like that. And so those are the four main industries I was thinking of. But now I'm going to start talking about. I'm going to leave it at those four and start talking about how the time it could be a relevant aspect to look at. And so I believe the assumed probability can be viewed in different ways with respect to time. So with the very initial example I provided, it was very kind of cut and dry, meaning that if the events never happened, we remove them from the assumed probability. And if they had, then okay, they're there and like they would be in the standard mathematical probability. But that's, from my opinion, that's more of that kind of more black and white thinking is more relevant in just more mathematical examples, but the sort of thinking now is going to be what I believe is more relevant for the real world examples. And so, let's see, let's get the next page of my notes. Let's see. Okay, so now we're going to have to assess being different time frame windows. So the first example is if things that have never happened ever. So let's say, like an example, if like something never happened you remove it from the assumed probability, or you remove it from the mathematical probability, and then you get the assumed probability after removing those events from the total ones that are possible. But you might be thinking, well, what happens if there was an event that happened, did happen, but it happened most recently 40 years ago? So let's say there has been events that have happened, but most recently 40 years ago. And so in this case, I would not think it is right to sort of remove those events from the mathematical probability, but instead there could be a certain weight attributed to these events and sort of getting what the assumed probability, or what I think like the assumed probability I say is a realistic probability as well. That's another way to think about it. And so there should be like a certain weight attributed to that, not so meaning that it's not completely removed, but it's also not just completely there as well. It's has a weight to it, but since let's say certain things happened most recently 40 years ago, I'll say 40 years ago, that's a long time ago, so they're probably not going to happen. But there is a chance. We have seen them before. We have seen them happen before. So there's going to be less of a weight on those things. And let's say a real world example, like in a certain area, maybe one time there was like very bad tornadoes that just severe damage to entire towns in a certain area, but that happened 40 years ago. And it's just kind of an isolated incident. So it's not right to, okay, let's just remove the potential for, let's just remove tornado damage from the sort of equation, but it should be sort of have less of a weight than other things because it is so rare. Or it has a weight because it has happened before, but it's so rare that it has sort of less of a weight than, let's say, a place has regular hail damage, then and they've had hail damage periodically every 5 years. That would have more of a weight in determining the different rates for insurance than tornadoes, and specifically that sort of aspect in homeowners insurance for that example. And so that was an example for, let's say, an isolated event 40 years ago. But then what about 30 years ago? What if there's an event that happened 30 years ago? So 30 years ago, that's still a pretty long time ago. I'm not even 30 years old, so it's even before I was born, but it's closer than 40 years ago. And so what should happen is the weight for the event that happened 30 years ago in these different with using the assumed probability as an optimization principle, that the weight from the event that happened 30 years ago is more than the weight that happened 40 years ago, but less than ones that would happen in like more recently. So the weight for a 40-year-old, like when there was a 40-year-old event, is going to be less than 30, and then less than 20, and then at that point, it's 20 years ago. That's still a while ago. That's sort of like a generation. That's still a while ago, but eventually there's going to be a point where so the weight gets larger and larger and larger. Eventually, I'm not sure where the actual line would be. That's another thing to analyze. Where's the line going to be when viewing the assumed probability as an optimization principle where, oh, an event happened maybe 15 years ago. Okay, that is going to remain at a value which has a weight the same as kind of anything that's happened 15 years to the present day. Maybe it's 10 years to the present day. That sort of weight could be the same for all those. And then once you get past 15 years, the weight starts getting less and less and less for that. And so, and obviously events that have never happened, they don't have a weight until they do happen. If they do happen, that's when you put them back into the probability calculus. Just if events that have never happened, then happens, and okay, now they're there, and they're there with a certain weight on them for good. Um, let's see, and so that's kind of I think the most relevant actually of this whole optimization principle is when taking it with like respect to time. Um, and so I've looked into this kind of thinking before to see if it's been done. And obviously, it's kind of hard to look up because I've made up the concept, the name of the concept myself at the being the assumed probability. And so I don't know if there's like a different name for something similar, but two things I've noticed that are kind of similar, specifically with the time, I've seen that's kind of similar to weighted averages. But this is with respect to time. Weighted averages are usually um, with respect to like a probability or something. This is like with respect to time, so it's similar to that, and then it's similar to a prior slash posterior probability distribution. But for those sort of distributions, the probability like changes after each sort of individual event. So, like for that, the example, like if let's say you have a random coin, your prior probability is half for heads, half for tails, because there's two sides of the coin, and then you're flipping this coin so many times, and let's say that the coin like keeps landing on heads. Every like 9 out of 10 times, like every you just keep flipping this coin, and every time you flip it 10 times, 9 times it's heads. So then the posterior probability, which each time it gets closer and closer and closer and closer to that sort of 90%, until a bunch of tails show up, and then it goes down. But that probability fluctuates after each individual event. You can kind of look at it from the scope of, you look after like 10,000 flips, and then you sort of just you can go straight to the what the posterior distribution is. But on the entire way there, the probability is going up and then down for like the different sides. So each individual flip affects that, whereas how the assumed probability is different is we're kind of assessing different groups of things as a whole. We're basically talking about different categories of events, and that's what I was talking about with the lottery example. Different categories of events and what happened the very next time. And so the values I was able to remove from the mathematical probability to the assumed probability were those like a group, just one specific group of events, and removed those. And then let's say if that happens, we take the group of events, put them back, and then we would have to reassess, and then you get a smaller group of events that you can remove. And so instead of taking it as each individual, it's more you can remove things as a group, or add things back from an entire group, and then that's how you get the sort of probability calculations. So yeah, I said in my notes here how I think about it is that with the prior posterior probability, the probability changes after each individual event, but with assumed probability, the observations are kind of, it's observed from more a holistic standpoint, more group standpoint. And so that's kind of all I have today. I just want to introduce myself again. My name is James Laughead, graduate from The Ohio State University with a Bachelor of Science in Statistics in May of 2022. And this again is my statistical idea called the assumed probability, and it's more so a demonstration of the style of thinking that I would be able to bring to a company. And so yeah, I hope to be able to talk with employers hiring analytical jobs in the future. I know that already some cover letters um, I've sent to different companies, I've sort of introduced this idea of the assumed probability as an optimization principle. But obviously, on a cover letter, I was not able to go very in depth on the idea because this entire explanation video has been over 30 minutes. And so I'm really not able to send that in a cover letter. I'm only able to kind of give the very, very basics. And so, yeah, I hope to be able to talk to some employers hiring for analytical jobs about just different ideas and how I thought up of this and maybe different applications and how what I'd be able to bring to the table to them as a company. And so, yeah, I'd just like to thank anyone who got this far for watching, and any employers. I'm really looking forward to being able to talk to you in the future.